We're going to introduce a new topic in numerical integration that is known as Gaussian quadrature. And in some ways Gaussian quadrature is like the Rolls-Royce of numerical integration, and we'll see why that's the case in a minute. Let's just quickly go back and have a look at the trapezoidal rule. So in the trapezoidal rule, two function values are calculated at the endpoints of the interval, and then an estimate of the integral is made, as in this figure here, given by this black shaded region. We can see that there's significant truncation error when we do this. What happens if we modify the requirement that we have to use the endpoints of the intervals? Perhaps we can choose some points in the inside of the interval which is going to give us a better estimate of the actual integral. And indeed that's what we do with Gaussian quadrature. The points where we evaluate the function are determined to minimize the error for a particular kind of approximating function. And you can see in this simple example here, if we were to choose these two red points here, draw the straight line that goes through them, we can see that there's a little bit of underestimation of the function here, but there's a little bit of overestimation of the function at the two endpoints, and that hopefully these overestimates and the underestimates will at least approximately cancel each other out. So that's the basic idea behind Gaussian quadrature. It's choosing the points at which you evaluate your function. I do need to add at this stage that you cannot use Gaussian quadrature for tabulated data unless the tabulated data has been chosen at exactly the right points that you need. And we'll have a look at how to figure out what those points are in just a minute. So all of the integration formula that we've looked at so far look like this formula here. So the integral from a to b of some function is equal to some coefficients or weights, ci, multiplied by the function values at some points xi. Most of what we've done, the xi are evenly spaced, and c usually follows some kind of repeating pattern. For example, in Simpson's 1/3 rule, they go like 1, 4, 2, 4, 2, etc., all the way up to 4, 1. We're going to do something that looks quite different to that here. To begin with, we're going to start with a particular integral to estimate, and then we're going to see how we change the limits of integration. So for what we're going to do here, we're going to assume that we want to integrate from -1 to 1. The reason for this will become clear. And we're going to specify the function that we want to integrate is f. With Gaussian quadrature, what we aim to do is we aim to write this integral here, which is in some sense exact, but it's a thing we're trying to calculate. We want this to be exactly equal to a summation of some coefficients ai, and these are usually called weights, multiplied by the function evaluated at a certain set of points xi, and these are usually called the quadrature points. Now, we want this thing to be true for a specified set of functions, and this will become clear as to exactly what I mean in a minute. But if we choose this exact equality here to be true for one set of functions, generally it will not be true for a different set of functions. The set of functions we want this expression here to be exact for are polynomials of degree less than or equal to 2n minus 1, where n is the number of points that we're choosing to use in this summation. So for this summation here, we're going to have n weights, and we're going to have n quadrature points. What this means is then, we want this expression here to be exact when f of x is equal to 1, when f of x is equal to x, when it's equal to x squared, x cubed, etc., all the way up to x to the 2n minus 1. Of course, if it's true for all of these individual monomials, it must then be true for any combination of all of them. This particular form of quadrature is called Gauss-Legendre quadrature. First of all, the integration limits are -1 to 1, and there is no additional function that appears inside the integral. So for things that we'll look at in a little bit, often there'll be some other function w of x inside here. For Gauss-Legendre polynomial, Gauss-Legendre quadrature, that is not the case. So this is the expression that we want to be true, and I've already mentioned this, that those are the weights and those are the evaluation, or what we call the quadrature points. I'm going to go through a very simple example of how to derive these things. Weights AI and the quadrature points XI for Gauss-Legendre quadrature, and we're only going to look at 2-point quadrature. So in other words, we're going to just choose 2 points. And we're actually not going to prove this. I'm going to get you to do this as a separate exercise, but we can prove that it's exact for polynomials of degree up to 2n minus 1. Because n is 2 here, that means it's exact for polynomials up to order 3, in other words, cubics. So, for n is equal to 2, our quadrature rule says that this integral is exactly equal to the sum from I equals 1 to 2 ai times f of xi, which is just equal to a1 times f of x1 plus a2 times f of x2. And so the a1, a2, x1, x2 are unknown. We don't know what those values are. That's what we're trying to find. So we need 4 equations, and we can get those 4 equations by, in turn, setting f of x equal to 1 in this expression here, then setting f of x is equal to x, then f of x is equal to x squared, and finally x cubed. And we'll end up with 4 equations that are linearly independent. So that's our 2-point Gauss-Legendre quadrature rule. Let's let f of x equal 1. So the integral from minus 1 to 1 of 1 is simply equal to 2. And if we substitute f of x is equal to 1 in this expression, f of x1 is just equal to 1 and f of x2 is just equal to 1, so we see that this then is equal to a1 plus a2. And so our equation, our first equation, is a1 plus a2 is equal to 2. We then go up to our rule at the top here and we say, okay, let's let f of x equal x. Well, the integral from minus 1 to 1 of x dx is simply equal to 0. And if we plug our function x into the right-hand side, we get a1 x1 plus a2 x2. So our second equation is a1 x1 plus a2 x2 is equal to 0. Plug in x squared. The integral from minus 1 to 1 of x squared is 2/3. We plug the function x squared into the right-hand side, we end up with a1 x1 squared plus a2 x squared, and our equation is a1 x squared plus a2 x squared is equal to 2/3. And finally, if we do the same thing for f of x is equal to x cubed, we end up with our 4th equation. So we have 4 unknowns and we have 4 equations. Now, if we solve these equations, and they're non-linear equations, we get that a1 is equal to a2 is equal to 1. In other words, the weights are the same and they're both 1. And that x1 is the negative of x2, and x1 is equal to negative 1 on root 3, so therefore x2 is equal to plus 1 on root 3. So what we have, the 2-point Gauss-Legendre quadrature formula is given by this expression here. So we can calculate the function values at minus 1 on root 3 and the function value at 1 on root 3, add them together, and we've got an estimate of our integral here. Now, because of the way that we put this together, this expression is going to integrate a cubic polynomial exactly. That's remarkable. We can integrate a cubic polynomial exactly with information from only 2 points. Compare this to the trapezoidal rule. The key thing here, however, is that the 2 points we choose are critical, and they have to be plus and minus 1 on root 3. Any other points will actually get a result that's wrong. We've just derived 2-point Gaussian quadrature, but of course there are other coefficients that exist for higher orders. If we change the order, in other words we change n, then the weights and the quadrature points also change. So this is the formula that we've just derived here. For n is equal to 3, we can see that we have 3 points. The quadrature points are symmetric around the x-axis, and they include x is equal to 0. The coefficients are also symmetric about the central coefficient, and we see that's a general behaviour. If there's an even number of points, we have pluses and minuses for the quadrature points, and exact symmetry in the quadrature weights. For an odd number of points, we always have 0, plus the other points are symmetric about the origin, and the weights are symmetric. These values are tabulated in a book, quite a famous book called Abramovitz and Stegen, known as the Handbook of Mathematical Functions, for n as large as 96. You also find these things at the websites such as Wolfram Alpha and other things like that. So, we've seen that Gauss-Legendre quadrature is exact for polynomials of order 2 to n minus 1. Why is this again? This is important that you remember this. So, a polynomial of order 2n minus 1 requires 2n unknown coefficients. Our right-hand side estimate of our quadrature rule has n values of xi and n values of ai. Hence, provided we're smart enough to figure out what these values are, we've got enough equations and should therefore be able to ensure that all of the expressions x to the 0, x to the 1, x squared, all the way up to x to the 2n minus 1, integrate exactly to 0. Therefore, our Gauss-Legendre quadrature will be exact for all polynomials of order 2n minus 1. I mentioned a little bit earlier that Gaussian quadrature often comes with weight functions, w of x, and in general this is the case. And so the general quadrature rules, so this is not Gauss-Legendre now, this is general rules, looks something like this. So the integral from minus 1 to 1, f of x times some weight function of x is equal to some set of weights ai multiplied by function values calculated at quadrature points xi. The weight function is usually chosen for a reason related to the particular problem that we're looking at, and we'll have a look at a few of these in a minute. The quadrature points xi and weights depend on both n and the weight function. So if we change the weight function, we've got to go away and recalculate the quadrature points and the weights. So Gauss-Legendre points and weights are for the weighting function is exactly equal to 1. But even for the cases where that's not the case, our resulting integral approximation will still be exact for polynomials of degree 2n minus 1 or less, because that is the way in which we define the coefficients and the points to ensure that this thing is satisfied. Just as an example of a few different weight functions here, turns out the intervals for all of these three things are minus 1 to 1. The weight functions are actually moderately complex for the Gauss-Jacobi quadrature. 1 on the square root of 1 minus x squared for Gauss-Chebyshev of the first kind, square root of 1 minus x squared for Gauss-Chebyshev of the second kind, and there's a whole range of other terms as well. Something about Gaussian quadrature, even though I said earlier that it's sort of the Rolls-Royce of integration because it really integrates a lot of things quite exactly, certainly all the polynomials, even though that's the case, the thing we have to take into account and always remember is that poor resolution is always poor resolution. If we compare Gaussian quadrature to other methods, Simpson's rule, trapezoidal rule, typically Gaussian quadrature will use a lot less function evaluations to achieve a given level of accuracy. The question is, however, will this always give us good answers? So let's look at this oscillating function here. It's obviously some kind of sinusoid. Do we think that 5-point Gaussian quadrature is going to work well and be appropriate in this case? So let's look at the 5 points that we might get and then look at the 5 functions. Well, clearly we're not picking up these oscillations in the function, so this is not going to give a good answer. It's even exacerbated by the fact that the quadrature points tend to be closer to each other towards the edges of the domain and further apart in the inside of the domain, so the central part of the domain is underrepresented in terms of its variation. So Even a higher order Gaussian quadrature technique for this example may be poorly resolved near the centre. So we're not necessarily going to get good results unless we're resolving the features in our function that we're trying to integrate. So you've always got to remember that. An alternative is to subdivide our domain. So instead of using one domain for this, we divide it into 3 domains. We then use 5-point quadrature on each of the subdomains, and we can see now with this we're actually starting to pick up more and more of the features. So we would expect this to give quite a reasonable result. The other way you can look at things is doing what's known as adaptive step size. So you in some way monitor how things are going and change the size of the intervals. So for example, if we had a function that's represented by this black line here, we can see that the gradients near the wall are vary significantly, whereas they don't away from the wall. So, sorry, other way around. Low gradient near the wall, we don't need very many subdomains there. High gradient away from the wall, we need a lot more subdomains here. So we can split things up in a way that gives us the best answers.